Hi, I'm Bradley Cheal and I'm a Professor of Nuclear Physics at the University of Liverpool. The topic of my talk is the question, how large is a nucleus? And I would like to tell you a little bit about my research, which involves measuring the sizes and shapes of the many nuclei known to exist, both stable and radioactive, using lasers. So let's start with the periodic table. The elements are arranged according to their properties and appear in blocks which corresponds to shells being filled, which the electrons occupy. The element is determined by the atomic number Z, which is the number of positive protons in the atom, and this is the same as the number of the negative electrons if the atom is neutral. So a copper atom, for example, has 29 protons. But there are also neutrons present, and these are neutral. Now, of the naturally occurring copper atoms, for example, some have 34 neutrons and some have 36 neutrons. So this makes a total of 63 or 65 nucleons, which we call copper 63 and copper 65 respectively, and these are known as two isotopes of copper. Only two exist which are stable, but many more exist which are radioactive in decay. The picture you see at the top left is an illustration of our current understanding due to the work of Rutherford. We have the protons and neutrons densely packed at the centre, called the nucleus, which is positively charged, and the electrons orbiting around. So firstly, how big is an atom? The picture shown is a strand of human hair under a microscope. You would have to magnify it 1,000,000 times so that the width is the length of a football pitch, even to make one of its atoms 1/10 of a millimetre wide. So what about a nucleus? We would then have to magnify by another 1,000,000 times, so 1,000,000,000,000 times, and make the atom itself the size of the football pitch, only for the nucleus to be 1 millimetre wide, lying at the centre. So an atom is 1/10 of a nanometre wide, or 10 to the minus 10 metres, and nucleus is on the femtometre scale, so 10 to the minus 15 metres. So first of all, how do we know that an atom has this structure? Rutherford suggested experiments where alpha particles, which are positive, were fired at a gold foil. At the time, J.J. Thomson had discovered the electron and had devised the plum pudding model. This had some positively charged matter distributed throughout the whole volume of the atom, with the negative electrons placed around inside. If this was true, what we would expect to happen is that the positive alpha particles would pass through with little deflection, even if we take a uniformly charged sphere. The repulsive force would increase, according to Coulomb's law, only until the radius of the atom was reached, and then decrease linearly inside. What was seen instead is that while most particles indeed travel straight through, some particles were not only deflected, but deflected backwards. The only explanation is that the positive charge is concentrated at the centre of the atom in what is now called the nucleus. So the alpha particle can continue getting closer to the centre of the gold atom and feel a much greater repulsion, even though the charge is the same. And of course, this also explains why only a few particles were deflected, because if this region is relatively small, then most of the alpha particles pass by further away, through the gulf of empty space that is the rest of the atom. These scattering experiments, using alpha particles, or better still, electrons, gives us our first indication of the size of a nucleus. After studying many nuclei, the radius seemed to approximately be given by the formula shown. So it increases with the total number of nucleons to the power of a third. Now, before we go any further, what does this tell us about the nuclear matter already? We can work out the density of the nucleus by dividing the mass by the volume. The mass is approximately given by the number of nucleons times the atomic mass unit, and if we take the formula for the volume of a sphere, assuming that's what a nucleus is, we can use our equation for the radius. As you see, the atomic mass number, or number of nucleons A, cancels and we get a constant. So for any nucleus, or any size, the density is fairly constant. Adding more and more nucleons doesn't act to compress the nucleus. This actually tells us that, unlike gravity or electrostatic forces, the nuclear force is a short range, and nucleons only act with their nearest neighbours. This is rather reminiscent of a droplet of water, and this is in fact the basis of one of the early models for the nucleus itself. Now, while the formula with a to the third is a good starting point, it is only an approximation. We don't have an accurate formula, and so to understand nuclear sizes, we need to measure them precisely. To do this, in my research, we take the atom as a whole. As you may know, the electrons cannot orbit the nucleus any old how, but in well-defined orbits, and the atoms are built up with the electrons occupying levels or shelves of specific energies, which is shown here. Now, when we have these electrons occupying levels of definite energy, we can promote or excite an electron to a higher energy level by shining light at it. A photon of light has energy hf, which is Planck's constant times the frequency of the light, and if, and only if, this matches the energy difference, the electron is excited. And one way of knowing this has happened is that when the electron falls back down again, a photon is emitted again. And as you see, that studying the frequencies required, this tells us about the energy levels of the electrons. Some of these frequencies, or wavelengths or colours, they're all related, are shown on the right for some example elements. To investigate them, we use a laser, but not any old laser like a red one or a green one, but one that is tunable. The one shown here can be used to produce light of any colour and from infrared to ultraviolet. We shine the light at the atoms and count the number of photons emitted, plotted on the y-axis, as we adjust, or scan, the laser frequency, shown on the x-axis. When we see a peak, that means the photons have an energy which corresponds to the separation of the electron energy levels. So by looking for what is known as resonant frequencies, we are measuring the energies of the electrons in an atom. Now these energy levels are very different for different elements, but do they depend on the charge of the nucleus only? To know if it depends also on the other nuclear properties, we consider measuring a chain of isotopes of an element in high resolution to see if we get the same result. To a first approximation, the electrons will feel a point charge with a potential given by Coulomb's law, and then this could be used in fancy calculations to work out the energy levels of the electrons. But of course we know that the nucleus, although small, is certainly not a point. So we would see the same potential according to Coulomb's law outside of the nucleus, but a deviation inside, which is shown. This gives us the real energy levels of the electrons, which we can measure by finding the correct frequencies of laser light needed to excite them. Now consider another nucleus of the same element, but a larger isotope. Although we are adding neutral neutrons, these shuffle the protons around over a larger volume, and in doing so changing the potential that the electrons feel, and therefore their energy levels. We can therefore measure the different nuclear sizes by measuring small changes in laser frequency required to excite the electrons. Here are some measured nuclear radii, or rather the mean square radius of the charged protons for some isotopes of yttrium. As you can see, we focus only on the differences from isotope to isotope. There are in fact several features to point out straight away. The dashed line shows how we would expect the radius to increase according to the model based on a droplet of water mentioned earlier. Furthermore, we are assuming here the nuclei are spherical, but as you can see, the data do not follow this trend. This is because the nuclei are actually not spherical shapes but deformed, and this increases the mean square form of the radius. Starting at yttrium-89, which has 50 neutrons, the nuclei are rather spherical, but as you can see they increase in deformation, until suddenly there is a jump, and the nuclei suddenly become more deformed into a rugby ball shape. Understanding why this sudden change happens, and how, is one of the aims of our research. Now the circular data points shown are for what is known as the ground states, or lowest energy states of the nuclei. Like atoms, they can also exist in excited states. These are shown now also with triangular symbols, and these seem to be generally larger than their ground states. One particular interesting example is for yttrium-98. Here we see the same nucleus taking on very different shapes, and therefore different mean square charge radii, depending on its energy state. The nucleus in its ground state is still relatively spherical, but in its excited state becomes very deformed into a rugby ball shape. Another important point of note is the yttrium-89 isotope. which importantly has 50 neutrons, and here there is often a dip observed in the radius. 50 neutrons is an important number in nuclear physics and is known as a magic number. Nuclei with magic numbers of protons or neutrons are particularly stable and spherical relative to their neighbours. This is rather like atoms being particularly stable with extra energy needed to remove an electron when a shell is full. It makes one wonder whether the nucleus is like a blackberry after all, when it also behaves like a beehive, with the nucleons themselves moving around occupying shells in a similar way to electrons doing so, yet somehow densely packed together. Using lasers to excite electrons, we also find out other things. Not only do the energy levels shift from isotope to isotope, in high resolution they are also seen to split into several levels, and therefore so do the peaks. This is because the nucleus behaves like a little bar magnet, which interacts with the magnetic field produced by the orbiting electrons. Measuring this tells us how the nucleons are behaving inside the nucleus. The splitting also tells us, independently, about the shape of the nucleus, giving us the sign of the deformation. We learn, for example, that the nuclei in yttrium not only go from spherical to rugby ball shape, or positive or prolate deformation, but in between look like Smarties, showing negative or oblate deformation. Many of the nuclei we have used as examples so far are not stable, and decay to create others, meaning that they do not naturally occur. In fact, of the 2,500 nuclei known to exist, and there are no doubt many, many more, less than 300 are stable. If we take yttrium from earlier, this has only one stable isotope, yttrium-89, but 29 which are radioactive and decay with a characteristic half-life. So to get a full understanding of nuclei, then we need to study also radioactive nuclei. To do this, we must produce them in a nuclear reaction and study them live before they decay. One way is to use a particle accelerator to fire high-energy protons at uranium, causing the nuclei to fission or to split into two. You may have seen this curve before, showing how this can release energy, but in this case, it is the reaction products we are interested in. Each uranium-238 nucleus may fission to produce a different pair of nuclei at random, and then with many fissions, a whole distribution of different nuclei is then produced, so we can study the ones we want. One such accelerator is a cyclotron. So we have two electromagnets producing a strong magnetic field, and this time, as the protons spiral around the magnetic field lines, they pass between two D-shaped electrodes with a high voltage applied. So passing from the D that is positive to the one that is negative gives the protons a kick, increasing their energy. The polarity is then reversed with a radio frequency oscillation while the protons are inside the second D, so that the negative D is now positive, and the positive one is now negative, and when the proton travels back to the first D, they receive again another kick, and so on. Now as the protons gain more and more energy, they spiral outwards and leave us a beam of fast particles of 30 megaelectronvolts, enough to cause a nuclear reaction. The cyclotron just shown is in the JYFL Accelerator Laboratory in Jyväskylä, Finland, one of the places where we do our experiments. It's a nice place by the lake, but cold in the winter. I've now experienced minus 35 degrees, and we travel by a twin propeller plane. In the lab, there is the IGASOL, or Iron Guide Isotope Separator online, which houses the uranium targets in a chamber filled with a helium buffer gas. The proton beam from the cyclotron passes through, causing fission reactions, and the fragments recoil from the target foils of uranium into the buffer gas. They are then literally blown out through a tiny exit nozzle in the form of a supersonic gas jet. The gas is pumped away to maintain a vacuum, whereas the reaction products, which are charged ions, are captured by electrodes and accelerated to 30 keV, all in under a millisecond, so we can study very short-lived nuclei. This beam of radioactive ions is then filtered by mass and sent directly to the appropriate experimental apparatus through evacuated beam pipes. The white cabin in the picture shown houses some of the lasers. Another place we work is the Canadian National Laboratory known as Triumph in Vancouver. Here the cyclotron is massive, producing protons at 500 MeV, and you can see a person doing maintenance work inside. The The magnets are so strong, taking a megawatt of electricity, that when you're upstairs, ordinary paper clips on my arm even stand up on their ends. Another place is I solder, or isotope separation on line device, which is the name of the isotope production factory at CERN in Geneva. Here the protons come from a synchrotron. Like in Uvascular and Triumph, the ion beam passes through a magnetic field which deflects the ions according to their mass. This way, the magnetic field is adjusted to filter the nuclei for a specific mass for study. And last but not least, we also perform laser spectroscopy at the GSI facility in Darmstadt. In this work, a linear accelerator, which is shown, accelerates not protons but heavier calcium ions. These then fuse, so not fission, they fuse with heavy lead atoms to make very heavy elements, such as nobelium, located at the bottom of the periodic table with 102 protons. This is now the heaviest element to have its electronic structure studied in this way, and therefore the nuclear structure. Anyway, I hope you've enjoyed my little presentation, and thank you for listening.